Whew. Well, on that note, over to you, Vanessa. I believe
Ah,
we have another guest coming to join us.
we do, Amit. Get excited. Okay, so a couple of things I have to say. First of all, Steve, you did an amazing job. Such great questions. Don't leave. I mean, I hope you're not
I'm
leaving.
still here. I'm still
Stick
here.
around, stick around. Okay. And thank you everyone so far. I'm super pumped for who is coming up next. And I have to do my due diligence and say that if you are watching and you are on social media, PMP has social media. So on Instagram, they are PM Project One. On Twitter, PMP Nonprofit. And on Facebook, just look up Prison Math Project. So again, really trying to build up that community so that we become a group of people invested in this cause from all over the place that can communicate via the World Wide Web. So it brings you my great pleasure to introduce Amit Sahai. I hope, am I pronouncing your name right? Thumbs up if I am.
Oh,
Sahai?
pretty good. Yeah, Amit. Yeah.
Well, Amit. Okay, so I am going to read a little bit of Amit's bio and tell you why I'm so excited, and you should be too. So Amit received his PhD in computer science from MIT in 2000. From 2000 to 2004, he was on the faculty at Princeton. And in 2004, he joined UCLA, where he currently holds the position of professor of computer science. His research interests are in security and cryptography and theoretical computer science more broadly. He is the co-inventor of attribute-based encryption, functional encryption, and indistinguishable obfuscation. And if you are wondering what that even is, so am I. You're not alone. Amit is kind of a big deal, and his research has been covered by several news agencies, including BBC World Service, Quantum Mag, Wired, and IEEE Spectrum. So here's the deal. I met Amit for the first time last week, and while he almost lost me at obfuscation, he quickly won me over with his kindness, thoughtfulness, and passion for making what's in his head make sense to everyone else, including me. So, I haven't said anything about myself, but I'm the founder of a tutoring studio called The Math Guru based in Toronto. We're worldwide on the internet. Our whole goal is to break down stereotypes around what it means to be a math person, to make the math community more inclusive. I have a quick story myself, which is that I failed grade 11 math twice, and I was told I wasn't a math person until I met a teacher who really believed in me. I got a 99, then I got 100 in calculus, and the rest is history. You know, meeting people like Amit really remind me what it really takes to make the math community more inclusive, to include more people in the definition of what it means to be a mathematician, and to do what all mathematicians want to do, which is inspire joy and wonder in their audiences. So we need to encourage mistake making, getting it wrong, and being curious enough to fail. And as a testament to what a great teacher Amit is, earlier this week he asked me if he could run the presentation he's about to give you guys by me, just to see if it made sense. So I'll be honest, at first I was like, what is happening right now? But the incredible thing about him is that he encouraged me to ask questions, not just any questions, as many questions as I wanted until it finally made sense to me. And I'm proud to tell you guys that as of this moment, right now, I could actually explain to you myself what modular arithmetic is, but don't worry, I will not do that. I am going to let Amit do that himself, and I will be right here asking questions that I probably still have and that I know some of you guys have too, because we need to normalize mistakes, questions, answers, and curiosity. I'll hand it over to you.
All right. Thank you, Vanessa, so much for that really generous introduction and just all the kind words that you said. And absolutely, first of all, thank you also for just volunteering to sort of be my student for the next half hour as we learn a little bit about something that just fascinated me and in fact was the focus of my PhD work, which is the idea of a zero knowledge proof. Okay, so a zero knowledge proof is a way for me to convince you that something is true without telling you any reason why it's true. You should have absolutely no idea about why the thing is that is true, and yet be truly, honestly convinced that it is true, right? And what fascinates me about this is that we think about mathematics because it is so beautiful, right? It lets us understand the universe around us. It has all these like incredible oddities and fascinating little things hidden inside them, like the Sierpinski, triangle that we've seen earlier today, and so many other things. And that's definitely something that drew me to mathematics, right? But the idea of doing something impossible with mathematics was something that always really fascinated me, and it's really been what I've devoted my sort of academic career to for the past couple of decades. And even that sort of goes back to magic tricks. So I remember when I was very little, I was 7 or 8 years old, I used to love magic tricks. And Mitchell would come, he would show me some interesting trick, and I would be blown away. I'd be like, wow, that's just so cool, right? And in my mind, I always imagined that there was some really deep, remarkable reason, why he's able to make, 4 aces show up in a deck of 3 cards, just amazing things. I thought, oh, there must be some really incredible, deep reason. And I was always really sad, actually, when I finally learned a little bit later in my life that most of those things are just sort of misdirection and sort of little bits of deception. And I always felt really let down, right? That there was nothing like deep and fascinating going on there. But it turns out that mathematics is deep and exciting and cool and accessible and understandable. And it actually lets us do things that seem impossible just through the sheer beauty and depth that is there in mathematics. I want to give you a little bit of a glimpse of that today with the example of a zero-knowledge proof. And I also want to mix it up a little bit. And instead of having slides, I'm actually going to use a whiteboard. And again, Vanessa, you're going to pepper me with questions, which is what I would really love to have happen here. So,
I'm really excited, honestly.
all right,
Let's
awesome.
do it.
So
Let's do it.
Let me go ahead and move over to my whiteboard.
And if anyone else has questions, you can put them, any of the speakers or anyone in the Zoom room can put them in the chat, but also to remember that there is a Google form. The link is on the PMP site where you're probably watching this right now. I will be checking out that form here and there. So feel free to put any questions in there and I will ask them on your behalf.
Excellent. Right. So again, I want to talk to you about zero-knowledge proofs, which is a way of me to convince you that something is true without giving you any idea about why it's true. So we're going to talk about zero-knowledge proofs about mathematical statements. And in particular, today we're going to think about zero-knowledge proofs about statements that regard the question of exponentiation. So exponentiation, of course, is something that we all learned back when we were students in high school or middle school or something like that. And what's exponentiation? It says I have some base b, I raise it to some power x, and I get the result y, right? And let's just sort of keep a running example. Suppose that b equals 2, x equals 3, right? Then of course 2 to the 3 is 2 times 2 times 2, which is 8, right? So great, we all know that, of course. And what's really cool about exponentiation is that it's efficient, right? We can compute exponentiation efficiently, okay? And that's really cool. That means that we can do it fast. And again, we all have calculators that can do this, so we know for sure that it can be done. And in fact, we all kind of know how to do it. It's just multiplication after all. We just can square a number and multiply to do any exponentiation we want, right? Now, we also all learned back in high school, potentially, or maybe younger, about the inverse operation of exponentiation, which we call a logarithm, right? So if I take log base b of y, then I get back x, okay? And of course, in our example, if we take log base 2 of 8, then we'll get back 3, right? And now, most of you probably don't know how to actually compute logarithms, but probably you're all convinced that we can do it efficiently, and indeed it is true that we can compute logarithms efficiently, because after all, your calculator can do it, right? So if you have a calculator at home and you press the log button and somehow it does indeed tell you the answer right away, right? And that's because there is an actual algorithm for computing logarithms very efficiently, okay? And and that's great, right? That's very interesting and fun and something that we know about exponentiation, right? But today we're going to do exponentiation a little bit differently, which actually changes the nature of the beast here, okay? So when we think about numbers, of course, we all know the number line, right? So we have 0 in the middle, 1, -1, 2, -2, and so on and so forth, right, in both directions. And it goes off to infinity in both sides, which is really cool, right? Really fun to think about such things. But there's another way of thinking about numbers that we call modular arithmetic. Okay, and so for today, I'm going to assume we have a prime number, p. Okay, and what we'll do is we'll take this number line and kind of fold it on itself. Okay, so we'll actually make it into a circle where we'll have 0 here, 1, 2, 3, and so on and so forth, right until p minus 1. But then we'll change the rules and say that if I add 1 to p minus 1, I just get right back to 0. Okay? So that's what we call, again, modular arithmetic and mod p operations, is when you add, let's say, 2 plus p minus 2, then you just get 0. Or if I add 2 plus p minus 1, then I'd get 1, right? Because it would get circle around back up to 1. Okay? And let's take
So a quick
Absolutely.
exciting, tell me if I'm right, because I was
Yes.
explaining this to a friend of mine and she was like, oh, it's just like a clock. A clock is mod 12.
Exactly. Yes.
And that I was so excited. I was like, that makes exact sense, especially with the visual.
Yes, absolutely. It's exactly like a clock with mod 12. The only difference today is that we're always going to make sure we're working modulo a prime as opposed to a composite number like 12, right? So, but you're absolutely right. And you can kind of imagine for today, let's keep the example of p equals 5, right? So there we have our number line, which is now this number circle, and it just has 0, 1, 2, 3, and 4, and then it circles back up to over to 0, right? And let's think about what happens now when we are working in this modular arithmetic situation. So let's take our example of 2 to the power 3, right? So 2 to the power 3 we know was 8, but there is no 8 anymore, right? So instead, we would end up with 8 minus 5, which is 3, right? Because we would circle around, get back to 0 at 5, and then we go 1, 2, 3, and then get to 8, right? So in fact, modulo 5, we have that 2 to the power 3 is equal to 3, okay? So, so indeed, we still have exponentiation that we can do, mod p. We can say b to the y equals b to the x, mod p, right? And it turns out that this is still efficient, right? Why? Because it's just the same algorithm, right? We all know how to do exponentiation. You just multiply. Just keep multiplying, keep squaring, right? And just the same algorithm works if you work modulo p, right? There's nothing that changes, and everything is still nice and efficient. Okay. However, it turns out that computing the equivalent of the logarithm, like the inverse operation, so log base b of y equals x mod p, this turns out to be really hard. In fact, we don't know what the fastest way of doing this is, and we, people like me who are cryptographers, really like this. Really like the fact that it's so hard, because, for example, if you have a prime that's really big, let's say it's bigger than, let's say it's 1,000-digit prime, right? So it's a really, really huge prime number. Then, in fact, if we had all the computers in the world trying to figure out what a logarithm like this is, it would take all the computers in the world well over a century to compute the answer. So it's just really, really slow. It's just really hard computationally to figure out the answer here, right? So this seems hard. It's not efficient anymore. Okay. And why is that interesting? Why do we care about that? Because it sets up a situation where there can be an information asymmetry, where there could be something that I know but you don't know. Okay. And that's kind of the situation we want for our zero knowledge proof. So let's go ahead and set that up now. Okay. So suppose that we have me and we have Vanessa. Okay. And I'm going to play the role of the prover in this situation, and Vanessa will be the verifier. Okay. And suppose that I know, so Amit knows this y, b, x, and p, right? So I know everything. I know exactly how we came up with y. You know, we had y equals b to the x mod p, right? But Vanessa is missing this sort of key piece of information. She's missing X. So she knows Y, B, and P, okay? And let's say what I want to do is I want to convince Vanessa that actually I know X. I know how to compute Y equals B, how to explain Y as being B to the power X modulo P, okay? And that's what I want to convince her of, right? So, and again, we're going to have this running example where, we have Y equals 3, B equals 2, and X equals 3, right? And we already checked that 2 to the 3 is actually 3 modulo 5. Sorry, P equals 5. Okay. So, all right. So before we kind of jump into it, let's just think for a moment. And we can see that if I want to convince Vanessa that I know X, well, there's a trivial thing I could do. There's like a thing I could do immediately. I could just send over X, right? If I just send over X, then Vanessa could check, right? She could herself compute. She could just compute B to the X modulo P, right? And just check, is it equal to Y or not, right? And if it works out, then she's definitely convinced that I know X because I just told her, right? And if it doesn't work out, then she knows I'm a liar, right? So she knows that I'm not telling the truth. That's easy, but of course that is our whole point was not to do that. Our whole point was to not just have Vanessa figure out what X is. I want to actually hide it from her and still convince her that Y equals B to the X, right? And we can kind of think about this as like X being my password, right? That X is something that only I know. I don't want to reveal it to Vanessa, but I want to convince her that I actually do know my password so that she like lets me into her secret society, right? So that's what we want to do. Does that make sense so far? Vanessa, you with me?
Okay, it is making sense to me. Don't worry, I'm not lost. I was actually marveling at the fact that I didn't have a question. I was
Okay.
like, okay, I actually really understand what's going on. So you did a really good job the first time, I'll just say.
All right.
Because I'm with you. And I think that's important too, because why wouldn't you just send X over?
Right.
That makes sense. Maybe it is a password, maybe it's a secret password. I just need to know
Right.
that you have it, but you can't
Right.
actually tell me what it is.
Right. I do not want you to know, right? I actually want to hide it from you. And again, it just seems crazy. It seems like I'm asking for something insane. Like it's my password. If I want to convince you that I know it, I have to tell you my password. After all, that's what we do every day. Like we log in and we just type our password, right? And it just gets sent over to the other website. But I'm saying, no, I don't want to do that. I want to do something that seems impossible. I want to convince you that I know X without telling you what X is, right? So, and I do think it's worth it to stop for a moment, just marvel at this, just marvel at what it is that we're asking for and how crazy it seems, how like unreasonable it sounds to be able to convince you that I know X without telling you what X is, okay? So, all right, now that we've paused for a moment and just marveled at it, let's
But it is like it does feel like a magic trick, which is so exciting.
yeah, right. It sounds crazy, and again, it's not. Trust me, I didn't just bribe Vanessa. She's not going to say, "Oh yes, I believe you," and that's why it's a magic trick. There's no deception going on. We'll just use math. We'll just try to figure out how to do this with only mathematics at our disposal. Okay. So here's what we're going to do. Okay, I'm going to get us started. Sorry. Before I get us started, let me just tell you about one little piece of information that we'll need to know, okay? And this is something called Fermat's little theorem. And don't worry, this is not Fermat's last theorem or anything too scary like that. It's Fermat's little theorem. I don't have time to prove it to you today, but if you're curious, you can just go to YouTube and type Fermat's little theorem proof, and you'll see many different proofs that people have posted on YouTube. So what does it say? It just says that if I take any base b and I raise it to p minus 1 modulo p, then in fact I get 1. Okay, and again, just as an example, if suppose we had 2 and I raise it to the power 5 minus 1, which is 4, so 2 to the power 4, this would be 4 times 4, right? which is 16, but modulo 5. So if we think of that modulo 5, sorry. Then in fact we get back, 16 minus 3 times 5, which is 1, as Fermat's little theorem requires. Okay, and it's just true whenever p is a prime. So again, here it's absolutely critical that p is prime. Okay, so p is prime implies that b to the power p minus 1 is 1. Okay, and now let's also remember that how do we normally get a 1 as a result of an exponent, right? There's only one way, right? Like if I want to start with b and I want to raise it to some power and get 1, how would I normally do that? Vanessa, how would I normally do this? What do you need to raise b to get 1 if you're just working?
You need a 0.
Just need a 0,
on, zero's
right?
on. Yeah.
Yeah, that's the only way to do it, right? You just raise it to the 0 and you get 1, right? So what Fermat's little theorem is kind of teaching us is that if we're working modulo p, then in the exponent position here, p minus 1 is our new 0. Or I mean, we still have 0, but p minus 1 is also 0. Sort of in the exponent here, whenever we go around to p minus 1, we've actually come back to 0. Okay, and we're just going to think about that a little bit as we ponder how to create this zero knowledge proof. Okay.
And okay, I'm not here to pressure you, but I know how excited we're all getting, and I'm just letting you know you have about 12 minutes, just so you mentally can prepare.
Excellent. All right, thank you.
No problem.
Very good. So, all right, so let's think about how we're going to do this. Okay, and the first step is that I'm just going to pick a random number. Okay, I'm going to pick a random number r from the set 1 to up to p minus 1. Okay, and let's just think again, keep our example running here. Let's say that we pick r equals to 2. Okay, and then I will compute z equals b to the r mod p. Okay, so again in our example, this would be 2 to the 2, which is just 4. We didn't even hit 5, right? So it just remains 4. Okay. Now observe that r has absolutely nothing to do with x, right? So far, everything I'm doing has nothing to do with my secret x whatsoever. And I just go ahead and I send over to Vanessa z. Okay, so again, in the example here, I've sent over z equals 4 to Vanessa. Okay. Now, what I'll ask Vanessa to do is just flip a coin. Sorry, flip a coin. Flip a random coin, either heads or tails. And she sends it back to me. Okay? And now what I will do is if the coin is heads, so if I get a heads, sorry, then I just tell Vanessa what r is. So I just send r. Okay? And note that Vanessa can now check that at least I didn't lie about z, right? She can check if z equals b to the r mod p. Right?
Okay, wait, I actually do have a question now.
Very good. Yes.
So because I was thinking about this. So do I know if I go heads, you go r? Do I know that information?
Absolutely. Yes. Everything about this is public, right? It's a magic trick, but I announce it ahead of time what I'm going to do.
And also, is it the same every time? So every time it's heads, you send r.
Every time it's heads, I always send r.
Okay, got it.
Right?
Thank you.
And again, this is something that Vanessa could easily check, right? She could just check that, oh yeah, indeed, 2 to the power 2 equals 4. Everything checks out, right? So great. Now, if that happens, if this is what happens, first of all, Vanessa definitely did not learn anything about x, right? Because nothing is even dependent on x so far, and she's been able to verify everything. Okay, so far so good. It's not clear why she should be convinced yet at all, right? Because we're not done yet. What if it's tails? So if, on the other hand, it's a tails, okay, then I'm supposed to send d equals r plus x mod p minus 1. Okay. And now what we'll do is we'll ask Vanessa to check that I did that correctly. What does that mean? She checks that b to the d equals z times y mod p. Okay. Now let's think about this. This may not be totally obvious, right?
What?
So what is b to the d? This is
Good. How are you, Shu?
this is b to the r, b to the x, right? And now we can just see that that's actually this works, right? Because b to the r was z and b to the x was y, right? So so again, this should be
Using
true.
exponent rules, everyone. Using exponent rules. I feel the need to clarify.
Very good. Using the standard exponent, right? B to the r plus x is the same as b to the r times b to the x. And so this works out, right? And again, let's just do the example. In the example, we would have 2 plus 3, right? R was 2. And if you remember, x up here was 3, right? And 2 plus 3, mod 4. So mod 4, that's just 1, okay? And here we would be checking that 2 to the power 1 equals 4 times 3. If you remember, y was 3 up here, and z was 4. And that's 12, but remember 12 minus 10 is 2. And so indeed, 2 equals 2, and it all checks out, right? So here again, we use the mod 5, right? When we're working mod 5, then we go around the circle twice to subtract 10, and we get back to 2, right? Okay, so very good. Presumably, at this point, hopefully you're following along, but you're kind of wondering, wait a second, why are we doing this? What just happened? Like, why did I say to do all these things? So I am going to claim to you now that, in fact, if we do this, if we follow this protocol, if we actually do things the way that I've suggested, then Vanessa becomes a little convinced at the end of this that I actually know x, okay? And in fact, if we do this, let's say 100 times, one after the other, each time with a new R, a new coin, and a new, like everything all over again, right? So not just this, but in fact even this, right? Then if I keep satisfying Vanessa in this protocol 100 times in a row, then she should be incredibly convinced that I know.
I'm impressed. At this point, I'm impressed. And I'm wondering, how is he doing it?
Right? How exactly? You should be wondering, how am I doing it? And of course, if I know x, then it's easy because like I've told you how to do it. Like I just do this, right? I either send r or I send r plus x mod p minus 1. So I've actually told you everything that I'm doing, right? It's just the fact that I have been able to do it 100 times in a row implies that actually I do know x. So let's just think about that. Let's think about each of these kind of criteria separately, right? So why should that be? If I can do this 100 times in a row, why should that mean that that in fact I really do know what x is? Let's just sort of stop and ponder that for a moment.
So this is the part I actually find interesting because
Yeah.
so I have a habit of over-explaining, which is why I keep saying, wait, this is because of exponent rules and this is because of this. But it's because I feel like it's often the small little things that if you pass over them too quick, all of a sudden the student, well, me at least, I'll miss the whole picture.
Absolutely. Yes.
Right? Like I'm like, I just need to know. So this part, I remember asking you, I was like, okay, hold on. It's like, I get it, but I don't get it. Why did this prove that you know X?
Yeah, right?
Why did it?
Right, and yeah, it shouldn't be obvious immediately. Maybe to some people it is, but generally speaking, it takes a little moment to sort of think about this and see why, right?
Mm-hmm.
And the main reason is that I won 100 times in a row, right? Like I convinced you 100 times in a row. If that's the case, I must have been ready to answer both heads and tails, right? If I was only ever ready to answer heads or only ever ready to answer tails, then there's no way I would be able to get through 100 of these experiments in a row without failing, without you catching me, right? So in fact, I must have been ready to send both R and to send d, which is r plus x, right? And if I can send both of these things, that means I must know r and r plus x mod p minus 1, right? And if I know both of these things, then that implies that I know, r plus x minus r, which is x, which is exactly what I was trying to prove to you, right? So
Bam.
this is the cool thing. That's what happens here, right? And just simple elementary mathematics in modular arithmetic, right? That allows us to establish this, that in fact I must know x, right? Like the probability that I don't know x if I went through this 100 times is 1 over 2 to the 100, right? So you're much more likely to be struck by lightning many times in a row, right? Than for me to lie to you in this game, right?
Yeah, I mean, it would be fairly impossible for you to get it. Well, exactly, just like you said. So, okay. Now, if anyone has questions, I know there's some action in the chat here. If anyone has questions, feel free to ask. Someone did ask, so wait, do I know X? And no, the point is, Amit is trying to convince me that he knows X. He's kind of like, no, 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 I know what it is. And I'm like, really? If you know what it is, then just tell me what it is. And he's like, no, I can't tell you what it is. It's a secret, but I can prove to you that I know what it is without revealing the secret. That's the vibe of the whole thing here.
Exactly, right? But let's actually engage with that question a little bit more. So why is it that you can't do this? For example, why can't you figure out what x is, like in this simple way? Why can't you do the subtraction? It's because you, Vanessa, you only get to see one or the other, right? You only see either r or d. You never get to see both, right? And obviously, if I send you r has nothing to do with x. Why should you, like, that gives you no information about x, right? But the point is, neither does r plus x, because after all, we chose r completely at random, right? We chose r
Can I ask
completely at
if
random.
I'm now
Yeah.
I don't think so, but maybe for some reason this is reminding me of linear systems. Like, is that at all a way I could have been checking to solve for X if I had more information, or not really? Am I off base?
Absolutely. No, you're absolutely right. Right. The point is, it's a really simple linear system. Like if you actually got me to answer both heads and tails, which I never will,
Right.
right? I
Right.
never do
Okay.
that, right? Then, like, there are two variables, r and x, and now you have two equations, and you'd be able to figure out both r and x, right? But I only ever give you one, right? You ask me at random, but I only give you one of the two equations, and giving you one equation is just not enough information, right? It's a line. And that leaves every single possible value of x open, right? There's always a value of r that explains every value of x. And you don't know what r is. I chose it at random, right? So since I gave you r plus x, or I just sent you r, both of these are just individually completely random. They give you no information about x, right? And that's why you're convinced that I know x, and you literally got zero information.
It's pretty
Absolutely.
frustrating. It's a frustrating place to be, I would say.
Right. It's frustrating, but also so fascinating,
It
right?
is.
Because it's something that seemed impossible, and yet we were able to do it just using some elementary, just really cute and wondrous mathematics.
I don't think I've ever heard anyone describe math as cute, but I love it. I am here for it. It is pretty cute.
Yeah, I don't know. I think math is incredibly cute, right? It can be incredibly cute, right?
I love it. Okay. All right.
And
This has been, no, keep on going. You've got a few more minutes. So say
okay,
whatever you want. We can
all right,
do some questions, whatever you want to do.
all right, excellent. I just want to say that this is just, the tiniest taste, right? And there's so much more here. And in cryptography, especially the kind of cryptography that I like to do, we can build upon these ideas, and you can in fact prove a whole lot more. You can prove much more than just that fact that I know X. You can actually prove almost arbitrarily complex statements in zero knowledge. I can convince you of incredibly interesting things without telling you anything about why it's true. And we can even apply this sort of idea to software. There's some kind of a notion of a zero knowledge software, where I can give you some software, and you can run it and it'll run, but you'll have no idea about why it works. and that's something that I've worked on for 22 years of my life, and really love thinking about. And there's just so much to understand and explore here. And yeah, definitely would invite anyone who wants to think about this to read and learn more about it, and share this sort of joy of this sort of figuring out how to do impossible things with mathematics.
Ah, I love it. Your joy is palpable. And basically, I mean, remember, almost every single thing in mathematics was once deemed impossible before it was discovered. So I love that. Now, okay, all of a sudden a bunch of questions are coming in, so I need
Awesome.
to hold you for 2 more seconds.
Absolutely.
Okay, first thing, somebody asked, can you ask what the computation is that you do to check him? Okay, so you did explain this, but so to whoever's asking, I get that this is a tricky one. He's giving me, I mean, why am I doing this for you? You can explain. You can explain.
Sure. Yeah. but you can, Vanessa, you can help me make sure I'm getting the question right. So if I'm understanding the question, you're asking me just to spend a little more time explaining what is it that Vanessa does, right? Like
Well, yeah, what do I do to check? So the first thing is that we're
Right.
doing this 100 times, but the second thing is what is the exact calculation?
Yep. So
And keep in mind, we have like 3 minutes.
okay, no worries. So so the point is, it's a different calculation if she flipped a head, and a different calculation if she flipped the tails, right? So if she flips the heads, then I send R, and she already knows Z. Remember, I sent Z in the very beginning. The very first message was Z. So she just checks this. She computes B to the power R mod P on her own, and she checks, is that equal to Z? That's it. That's all she does in this case. Okay. And in the other case, that's the easy case. Maybe that wasn't the one that he was curious about, or she was curious about.
Well, no, I think the point is that there's two calculate. That's the point. I have to do both. I have to do one each time depending on what you send over. And because I do those calculations so often and you're right every time.
Yes, that's what makes it so convincing, right? And the other case is just here. So the other case is just this, that Vanessa will compute B to the power D. She'll also compute Z times Y mod P and just check if they're equal to each other, right? And that's it. She does this 100 times, once for each of these iterations. And if it all checks out, then she has to be convinced, because she's like, wow, there's no way he could have gotten so lucky. There's no way that
I mean, unless it is magic, I guess. Unless it's actually magic.
Yes, unless I could actually read your mind or violate causality, right? Like if I could actually read your mind and know what your coin is, not even read your mind, I would have to somehow predict the future, know what coin you're going to flip, right? And then like base my first message on the coin that you would have predicted, that you would have gotten, that you would have flipped later in time, right? So
that would be a lot. That would be a lot, to be honest. Okay, he also wants to know if you can convince him that Fermat's last theorem is true without revealing the proof.
Indeed, I can. Indeed.
What? Okay, wow.
So if Fermat's last theorem, everyone knows because it's published. But let's say that I proved one of the other famous conjectures that are still open. For example, the P equals NP conjecture, or the P not equal to NP conjecture, which you may not know about, but that's all right. Just some conjecture. Let's say Fermat's last theorem, just to follow the question. I could have an entire proof written out. I don't want to show it to you, right? I could actually encrypt the proof and then prove to you in zero knowledge using these kinds of tricks and many more. There's more to this. I could actually prove to you that I have a valid encrypted proof of Fermat's last theorem, and you would have zero idea what the actual proof is.
Incredible. Incredible. Is he a mathematician? Is he a magician? Who knows? Who knows? You are amazing. Honestly, we need more mathematicians that just encourage question asking on any level. It really made me feel really welcome. It made me feel excited to learn something. It took away the intimidation around it, and it was great.
Awesome.
So thank you.
I'm so glad. All right.
All right. Well, awesome. Thank you so much for being here. If anyone wants to contact you, oh, you're gone. Do you wanna anything?
Sorry. Yeah, no, I'm definitely still here. Yeah, you can definitely send me an email. You can just Google my name. And actually, I really do want to encourage everyone to go to the Prison Maths Project website and think about volunteering and reaching out to a community that really doesn't have much access to people who love mathematics like we all do.
Amazing. Thank you so much.